Good evening, everyone. My name is Aditya Sharma, and this is Aircraft Propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program, that is National Program on Technology Enhanced Learning. And the course ID for this course is NOC 25-M147. The instructor for this course is Professor Vinayak Kulkarni, affiliated to Department of Mechanical Engineering, IIT Guwahati, and I also am affiliated to Department of Mechanical Engineering, IIT Guwahati, as a research scholar here. So we are into week 5 of this course, and pertaining to week 5's content, we are conducting this live tutorial session. So the topic that we will be discussing in this week's content is stagnation conditions and real cycle examples. So stagnation conditions in your Brayton cycle, that is gas turbine cycle, and then in the reality how the cycle is and examples related to that. We have been introduced to the real cycle examples. And the contents of this session are as follows. As has been given on your screens, total 4 lectures are there in this week's content. Lecture 13 to lecture 16. Okay. So before starting, let's wait for a few minutes to see if somebody joins. After that, we can start today's session. Okay, so we can start with today's session. So I was talking about the contents of this particular session. So 4 lectures are there. Week 5, lecture 13 to lecture 16. Lecture 13 is examples of gas turbine attachment. Attachments like intercooler, your heat exchanger. Yes. So these attachments we have seen in previous week's content, right? Yes. Attachments like heat exchanger. One more was there, which was reheater. Yes. And then intercooler. Okay. After this, we have lecture number 14, which is on stagnation conditions, the real Brayton cycle with stagnation conditions. So before this, we have been neglecting some things while we are analyzing our Brayton cycle, okay, related to your working fluid. So things like potential energy of air or kinetic energy of the working fluid. Okay, but in reality, it is not like that. So at some point, if we want to discuss the real scenarios, we'll have to include some assumptions we'll have to now remove from this point onwards. So this is related to that only. Then there are questions related to both the lectures. Okay, lecture 13 and 14. Then is your lecture 15, polytropic efficiency of compressor and turbine. So we have seen what is isentropic efficiency of turbine of the compressor. But then if we want to compare compressors, different compressors related to different compressors having some pressure ratios and then efficiencies, isentropic efficiencies. So these two things are not comprehensive to compare two different compressors. Okay. In that case, your polytropic efficiency comes into picture. That helps us to decide better which compressor is better. Okay. So this is polytropic efficiency. And then is examples of real cycle. So this is basically numericals, lecture number 16, and then lecture number 15 and 16 questions based on lecture number 15 and 16. Basically, like the questions will be on lecture number 15 as per the assignment. If you see questions on Lecture number 16 will come, I believe, later. Okay, let's see what we have first. So lecture 13 is numericals. Lecture 14 is stagnation conditions in Brayton cycle with stagnation conditions. What is basically a stagnation condition? We can understand it with the help of flow in some pipe. Okay, let's say we have some flow in some pipe. So I've drawn some pipe in which so the pressure that you will see at the walls of this pipe, this basically is your static pressure. Okay. Now let's see, this is point A, this is point B. At point B, what you will see is your flow has stagnated. Okay. I hope you understand stagnation. So it has stopped at point B. So at point B, then the pressure that we observe is the combination of two pressures. One is your static pressure, P1, plus your dynamic pressure. Okay. Which basically includes the velocity component. Because of the velocity of the flow, you'll have some pressure. Right? So this is your dynamic pressure. And these two, when combined, gives us what? Stagnation pressure. This basically is the stagnation pressure. So from here, what is stagnation condition? Where your velocity is zero. At point P, your velocity is zero. So this dynamic pressure that we see at point B with static pressure is your total basically pressure or stagnation pressure. And the condition at B is your stagnation condition. Okay. So this basically is difference between your static and stagnation conditions. Then is your isentropic relations. So isentropic relations will give relation between your static and stagnation conditions. So we have been using isentropic relations a lot in our numericals in the past. Then isentropic relations. So P naught is for your stagnation condition, P is for your static condition. So pressure when related to temperature, we can write this. This we know, just we are revising it. Then if there are two pressures, if the process is isentropic, in that case, from state 1 to 2, if it is going, the relation will be like this. Same is true for your this relation. Then for your density, the relation goes like this. One by gamma minus. Okay. So rho 2 by rho 1 also you can do. Okay, rho 2 by rho 1 is T2 by T1, 1 by gamma minus 1. So these basically are your isentropic relations. All right. Then next is your heat and work interactions in total conditions. So previously we have been seeing heat and work interactions excluding the dynamic part or the velocities of the working fluid. We have been neglecting all this. Okay. But in reality, there are velocities involved. So now considering all these velocities, what becomes important is not just the static part, but the total part. Okay. The total value of the parameter of the property that we are discussing. So in 14.2, we have compressor work. Then is your combustion chamber heat addition, then turbine work. So these three major topics are there, considering the total conditions. So let's see these one by one. First is your compressor work. So diagram goes like this. Temperature entropy from 1 to 2 dash. One to two is real for static. This is total. Initially, the total condition is O1 dash. This is O2 dash. This is O2. Okay. Now, if you have to see the compressor work, so these, if you see this difference, what is this difference? This difference basically is V1 square by 2 CP. What is this difference? This difference basically is V2 square by 2 CP. The dynamic part that I was discussing. Then initially this is the enthalpy. So previously we were considering only static enthalpies. Now these are total enthalpies. H01 at H02 we have this. Okay. And if you have to split this, H1 is 1 square by 2. This is 2. So from here, now compressor work can be calculated. Okay. And if you talk about efficiency, isentropic efficiency of your compressor, so one formula that comes out of here is H02 dash minus H01 divided by H02 minus H01. So this basically is the isentropic efficiency of your compressor. So at present, I am discussing the topics involved in your lecture number 14. After that, we'll see numericals. So from here, one important formula that comes out is expanding this. One important formula that comes out is E naught 2 equals to E naught 1 this. Okay. Then next topic is combustion chamber heat addition. So one important point here is that while there is heat addition taking place in your combustion chamber, it accompanies pressure loss in your total pressure. Okay. So if you have to show this with the help of diagram, so this is your compressor. Okay. So we have this 1, 2, this is 0, 3. This is total pressure is this. Okay. If this line basically is not your compressor line, but from static to your total condition. Okay, so this is your static state. This is your stagnation state at the exit of your compressor. So this loss. So this is your combustion chamber. So here the pressure P2 is not equal to P3. P naught 3 is less than P naught 2. Okay, so there is loss in your total pressure. So this basically is your loss in total pressure while the heat is added. And then heat and work interactions. How we write it? We write it as H naught 2 plus Q23 equals to H naught 3 plus. So this part is 0. No work is involved. Implies Q23 is H naught 3 minus H naught 2, which is H3 plus B3 square by 2 minus H2 minus B, sorry, square by 2. So this is, there. Okay. with this. Then if we see turbine work, so in case of turbine work, if the expansion takes place from 3 to 4, okay, expansion takes place from 3 to 4. In that case, heat and work interactions, we write this way: H03 plus Q34 is equal to H04 plus W34. Now, heat, there is no heat involved here, but work output we get. Okay, so W34 is H03 minus H04. Okay. So this basically is your work, turbine work. Then is isentropic efficiency of turbine has been discussed. Isentropic efficiency of turbine basically is the work that we got and the work that we should have got if the conditions had been ideal, or ideal is isentropic. So this is there. Then from here T03 we can predict. The formula is this. This can be easily worked out. If you face some issue, you can just comment in the comment box and I can reply there. Okay, so this is your heat and work interaction at each stage of the working fluid. So up to this point, we have discussed 14.2.6. Now is your the whole real cycle, how it looks like. Let me draw this after this. Okay. Move on to questions. It is like this. I hope this is clear. What is this? This is your compressor. Okay. This is your heat exchanger. This is your combustion chamber. This is your turbine. Okay. Again, here your heat exchange. Exchange is here, right? So in reality, your Brayton cycle looks something like this. Okay. Then moving on to questions. So first question we have here is this. Based on stagnation conditions, this question is there. Question says that if an aircraft is flying at Mach number 0.58 and the speed of sound is 330 meter per second, the stagnation temperature of on the nose of aircraft is R has been given, gamma has been given to us. So how we will solve it? So static temperature has been given to us. So related to your static temperature, stagnation temperature we can calculate. Okay. What is given to us? Back is given as 0.58. Then speed of sound in the medium has been given to us. Then gas constant has been given as 287 joule per kg Kelvin. Ratio of specific heat Cp by Cv is 1.4. Then if you want to find out this is 2 to find T naught, what we can do, we can use this relation. T naught by T is 1 plus gamma minus 1 by 2 m square. This is your relation. But here we know m, we know gamma, we know T. So T naught we can calculate. T has not been given explicitly, but because we have been given A equals to 330, implies A basically is gamma RT. Squaring both sides, 330 square by gamma R is your T. So if you calculate this will come out to be please calculate this. This will come out to be around 271.03 Kelvin. So T naught by T is 1 plus gamma minus 1 by 2, 0.58 square plus T naught is equal to 271.03 into 1 plus 0.4 by 2 into 0.58 square. So this comes out to be 289.23 Kelvin. Okay. So this basically is your answer. Okay. $289. Then we have next question. Please read this question. Then we can try to solve it. Okay, so let's see the question. The question is a high-speed subsonic airplane is flying at, so we have a plane flying at Mach 0.75 at standard sea level. The pressure at the stagnation point on the nose of the plane is. Now we need to find out the pressure. So stagnation pressure, sorry, static pressure and static temperature both have been given to us. We can calculate this. Given to us is Mach is 0.75, 01 bar. Temperature is 288.15 Kelvin. Gamma is 1.4. Then now using the isentropic relation P naught by P is, because we know this is equal to T naught by T gamma by gamma minus 1, and T naught by T is 1 plus gamma minus 1 by 2 m square. So P naught by P is 1 plus gamma minus 1 by 2 m square, gamma by gamma minus 1, 1 plus 0.4 by 2, 0.75 square, gamma is 1.4 divided by 0.4. So please solve this. Let's see how much we get as our answer. I'm getting 1.452. This I'm getting. Implies P naught is 1.452, 1.01. So this will come out to be 1.46 or 1.46. So this is your stagnation pressure. .46 bar. Because all the ratios, all the pressures have been taken in bar. So this is your answer, 1.46. 1.46 is the answer. Then let's move on to next question. Five questions are there, and information related to those five questions has been given. So let's have a look at what is given to us. So in an open cycle constant pressure gas turbine plant, so the gas turbine is open cycle. So gas exiting the turbine will not again somehow come back to compressor. So same working fluid will not keep on moving. Essentially, the same working fluid will not keep on moving in this cycle. In an open cycle constant pressure gas turbine plant, air enters at, so the entry first condition is given to us. T1 is given, T1 is given. The cycle consists of two-stage compressors with perfect intercooling and single stage. So perfect intercooling has been given. Two compressors are there and perfect intercooling has been given. And a single stage turbine with exhaust heat exchanger. So in this cycle, heat exchanger has been used and the turbine expands the gas in single stage. The cycle is limited to a maximum pressure ratio. The pressure ratio of combined compressors or single turbine is 7, and maximum temperature, that is the exit of combustion chamber. The maximum temperature is given as 1150 Kelvin. Then respectively was not required here. The isentropic efficiency of each compressor and turbine is 88%. Okay. And then effectiveness of heat exchanger is 70%. For maximum work output, so if the work output is maximum, we need to solve the following questions. And for air, we have to take the specific heat at constant pressure as this 1.005 kilojoule per kg Kelvin, and gamma we have to take as 1.4. Okay, so now we will do questions. But before starting to solve these questions, we'll just take a short 5 minutes break. After that, we'll start again, continue with the session. Thank you. Let's continue with the session. First of all, we'll write what has been given to us. We'll draw the diagram. After that, we'll take the questions. So for, for question number 3 to question 7, what is given to us? Given is inlet pressure for the compressor is 1 bar. Inlet temperature is 310 Kelvin. Pressure ratio combined for both the compressors is 7. Maximum temperature that is at the exit of combustion chamber is this. Efficiency of both the compressor, low pressure, high pressure is this. Efficiency, oh sorry, and is equal to turbine efficiency, this. And at last, epsilon, right? Effectiveness of heat exchanger is 0.70. Then let's draw the diagram. This is your first compressor. This is your second compressor. This is your turbine. If you want to, 2 is your first compressor, P24 is your second compressor, 4 to 5 is heat exchange, 5 to 6 is combustion chamber, 6 to 7 is your turbine. Okay, then for perfect intercooling, one equals P2 by P1. First pressure ratio is root of the whole pressure ratio. Okay, because P4 by P3 will be equal to P2 by P1. In that case, because P1 is 1, so P2 is equal to 1 dot root of RP. This is root of 7. So this comes out to be 2.64. Now the first question here is, at the exit of high pressure compressor, we need to find out temperature. So how do we do this? You see, for perfect intercooling, your temperature at the exit of first compressor is equal to temperature at the exit of second compressor. So T2 will be equal to T4. And if somehow we can calculate T2, we have T4 with us, which is what has been asked in the question. Then, so this is question number 3, right? So for perfect intercooling, T2 is equal to T4. Now to calculate T2, what we can do? We have been given the efficiency as 0.88 and the efficiency of compressor, first compressor, low pressure compressor can be written as this. This is known to us, 310. T2 dash is not known to us. T2 we need to find out. This is of concern to us. This we don't have. This we have. Okay. Then also using isentropic relation for first compressor, the two states T2 by T2 dash by T1 is equal to P2 by P1. Gamma minus 1 by gamma. P2 we have as 2.64. This we have, this we have, this we have, this we have. T2 dash we can find out. P1 is 310. P2 is 2.64. P1 is 1. So this becomes 0.4 divided by 1.4. I hope this is clear. If you solve this, please solve this. This is coming out to be 409.09 Kelvin. Okay. Then putting this here, we can calculate. Okay. This 1, 2, 3, using 3 into 0.88 is equal to T2 dash minus T1. T1 is 310 divided by T2 minus T1. From here, we can calculate T2. Implies T2 is equal to, so please calculate this. So I'm getting 422.6 Kelvin. So this is the answer for your first question. $422.6 Kelvin. The next question is total work consumed by compressor. Question number 4. Solution. I hope this is clear because T2 is equal to P4. That is why the answer. The compressor work. Total compressor work. WC is low pressure compressor plus high pressure compressor. Because perfect intercooling, both the works will be same. And this can be written as this. Now if you place the values here, P2 is 422.6 minus 310. So this will come out to be approximately this will come out to be 2 to 7 kilojoule per kg. Okay, 2 to 7 kilojoule per kg. The next question is work ratio, back work ratio. Now, work ratio is W net by WT, back work ratio is WC by WT. But do we have W net? For W net, we need WT. Do we have WT? We don't have WT. For WT, we need T7. Now we need to calculate T7. So 5 work ratio, or I'll start with calculate T7. T6 by T7 dash is equal to T6 by T7 dash. This is your isentropic relation. From here, you will get T7 dash. Okay. And T6 is given to us. T7 dash we will calculate from here. T7 dash is equal to T1. Of P6, how you will calculate? So P6 basically is equal to P4. Is that clear? P6 is equal to P4, right? And P4 by P3 is equal to root of RP, right? And your P3 is equal to P2. This you know. From here, you can calculate P4. Okay. And P4 is equal to P6. And if you work this out, this will come out to be around 659.54 Kelvin. And from your efficiency of turbine, isentropic efficiency of turbine, this is this. So T6 we have, T7 we need to find out, T7 dash we have, T6 we have. This is 0.88. So if you work this out, this will come out to be 718.39 Kelvin. Okay. So this is your T7. Then why are we doing this? Because we need to find out work ratio. Now turbine work WT is equal to, so this is your T7. Turbine work is equal to Cp T6 minus T7. 1.005 T6 is 1150. T7 is 718.39. And if you calculate this will come out to be 433.76 kilojoule per kg. Okay. Then W net is work for your turbine minus work for your compressor. Four 3.76 minus work for your compressor. For a compressor is 227. So this will come out to be around 207 kilojoule per kg. Now we can find out work ratio. Work ratio is equal to W net by WT. 207 by 433.76. So this will come out to be 0.477. And then back work ratio. We have to calculate. This will come out to be WC by WT. WC is 227. WT is 433.76. So if you calculate this will come out to be this much. 0.522. 0.477, 0.522. Okay. This is the answer of question number 5. Now heat input into the combustion chamber is Q in combustion chamber is T6 minus T5. 1.005. T6 is 1150. T5 we don't know, but we know effectiveness. Effectiveness is T5 minus T4 divided by T7 minus T4. Okay. From here, you want to calculate T5. T4 we have calculated 422.6. T7 we have calculated here. Now if you place the values, this will come out to be around T5 will come out to be around 629.713 Kelvin. Okay. So this we have calculated, this we have calculated, this is 0.7 given to us, and this T5 can be calculated. Okay. Then Q in, if you calculate, this will come out to be around 522.88 kilojoule per kg. This is heat added. Then the last question of this lecture is thermal efficiency. So thermal efficiency is W net by Qn. W net we have, Qn we have. So this will come out to be around this 13.6%. This was your question number 7. Then moving on to lecture number 15. Lecture number 16 is numericals. Lecture number 15 is polytropic efficiency of compressor and turbine. So this is important topic. Okay. So in the lecture, if you see, this has been discussed that if you want to compare two compressors or two turbines on their efficiencies. So if two compressors have different pressure ratios and then their efficiencies have been given to us, then how can we compare the efficiencies? How efficient one compressor is, how efficient second compressor is, how can we do that? Okay, because pressure ratios are different. And corresponding to the pressure ratios, efficiencies have been given, isentropic efficiencies have been given. But then if you want to then compare these compressors, we cannot do that, right? In that case, what we do is we concentrate on infinitesimal change. So for infinitesimal change in pressure, what is the infinitesimal change in your temperature? And based on these infinitesimal changes, we calculate the efficiencies. And these efficiencies we call as polytropic efficiency. Okay. So topics are there. This is important topic. I feel this is important topic. From the perspective of knowing this subject in a comprehensive manner. So topics are dependence on pressure ratio, then polytropic efficiency, in polytropic efficiency, we will first mathematically infinitesimal temperature changes have been given for both the isentropic change and for your polytropic change. Then efficiencies of both the turbine and compressor have been given. So dependence on pressure ratio. So first is dependence on pressure ratio. Lecture number 15. Isentropic efficiencies. Dependence on pressure ratio. How? If you see NT, this can be written as 1 minus T4 by T3 1 minus T4 dash by 2 T3 or 1 minus T4 by T3 divided by 1 minus pressure ratio T3 gamma minus 1 by gamma. This is it. For your turbine, this is there. Then for your compressor, this is there. Or RPC gamma minus 1 by gamma minus 1 divided by E naught 2 E naught 1 minus 1. So this is this PS. This 1, 2, 3, 4. If it is like this. So from here, not 2, not 1, not 3, not 4. From here. So if you see these two, this and this, your efficiencies are related to pressure ratios. Okay. This one has given example. So RPC is shown like this. So if efficiency is this, right? And this is this. This is and this is this. Now in this scenario, to compare these compressors, we cannot comprehensively comment on the performance of these compressors. Okay. In that case, what we do is we use polytropic efficiency. If you see this, these and these, if you see, here we are concerned with the first and the last states in the whole process. For compressors, if you see T1 to T2, 1 to 2, not 1 to not 2. For turbines, not 3 to not 4. Okay. But in polytropic efficiency, what we do is we see the infinitesimal changes. For these small changes of pressure, what are the temperature changes? This is what we see. So from here, so from this topic, so infinitesimal temperature change, if you see, polytropic efficiency. Here, infinitesimal temperature change. So for isentropic process, EV gamma is constant and dT dash change in temperature is equal to -1 minus gamma by gamma dT by T. So with respect to pressure, what is the temperature change? This is P into temperature. So this is for a polytropic process, the index is N. In place of gamma, we have N. Okay. And here your dt is N minus 1 by N dt by P T. But if you have to give for turbine, polytropic efficiency for turbine. First for turbine. So this is, if we represent it with NTP, yes, this basically is real work output, ideal work output. Yes. So this is CP dt CP dt dash. This is your polytropic efficiency for your turbine. And now placing the values of dt and dt dash. So NTP becomes n minus 1 by n into gamma by gamma minus 1. It becomes this. Okay. So this basically is your for infinitesimal change. This is your polytropic efficiency. Now, based on this efficiency, if you want to compare the two turbines having different pressure ratios, what we do is we bring the pressure ratios of both the turbines into a single pressure ratio, and then their polytropic efficiencies we compare. This way it becomes possible to compare both the turbines. Okay. Then we have for compressor. If we want to relate our polytropic efficiency with our isentropic efficiency, that also can be done. Okay. So the relation between isentropic and polytropic efficiency. है ना? So this can be done this way. So because your this efficiency is 1 minus T naught 4 by T naught 3, 1 minus 1 by RPT, gamma minus 1 by gamma. Okay. Now what we can do? Now T naught 4 by T naught 3. So this is your real process. Okay. So this, if you take as polytropic process, in that case, having an index as n, so this becomes this. Now placing this in NT, we get the relation between because this can be written as this NTP. This basically is the relation between the isentropic and polytropic efficiencies. Okay. Then same thing is for your compressor. Polytropic efficiency for compressor. NCP is the same way. So this is Ideal work input by real work input. CP D P dash by CP DP. And CP will become gamma minus 1 by gamma into n by n minus 1. Okay. So this is your polytropic efficiency for compressor. And then relation between isentropic and polytropic efficiencies. So this can be given. So NC is equal to, so like we did with turbine, same way we can do it with compressors. And here gamma minus 1 by gamma 1 by NCP minus 1. So this is it. These are the polytropic efficiency. 10. There are two questions. This is done. Then let's see question number 8. It says that for a given gas and polytropic efficiency of compressor, the isentropic efficiency of compressor dash with increasing compression pressure ratio. Four options have been given. So it increases, decreases, initially increases, then rests constantly, remains constant. What happens? The graph goes like this. NCRPC goes like this. For some, uh, sorry, for some, what? For some NCP, for some polytropic efficiency, single polytropic efficiency, it works like this. So if you have to compare two compressors, what we do is we bring their pressure ratios to a single pressure ratio, and then we compare their polytropic efficiency. So decreases, okay? B is the correct answer. Polytropic polytropic efficiency of a turbine is defined as the ratio of this is polytropic work output to ideal work output. Essentially, this Cp dt, okay, and Cp dt dash, this for turbine, for NTP, this is there. So this is your isentropic, this is your polytropic. So B is the correct option. In that case, we are done with today's session. So I'll conclude this session. There were 4 lectures. 2 lectures were based on numericals only. And then lecture number 14th and 15th, and 14th and 15th lectures, there were concepts. But lecture 15 was all on polytropic efficiencies to compare the compressors or different turbines. And lecture number 14 was on stagnation conditions, basically, and what a real cycle basically looks like. Okay. And then we saw numerical questions based on your attachments of Brayton cycle, and a few numericals, 2 numericals on stagnation conditions, and then 2 questions we saw on polytropic efficiencies. So this is it for today. Next session again will be on coming Tuesday with same timing 6 to 8 p.m. Thank you for watching this session. Bye.